This is part 2 of Huffman tree and priority queue. In this video, we discuss the implementation in C, C++. In the previous video, we discussed that a Huffman tree can be conveniently constructed using a priority queue. We just need to insert all the nodes into a priority queue. We treat the priority queue as a black box, and we know that the element with the highest priority always comes out first. Here, we associate the key or priority with the symbol frequency. The smaller the frequency, the higher the priority. So we delete 2 nodes from the priority queue, which will always have the lowest frequencies. We merge these 2 nodes to obtain a new frequency and put the merged root node back to the queue. We repeat the process until the queue is empty and we have a single tree. The last node deleted from the queue is the root of the tree, which is a Huffman tree. By traversing this tree, we obtain the Huffman code. We have discussed in detail the implementation of a priority queue in a previous video. Let's review it very briefly here. Record is a data record, where key is the key of the record, which is the priority. X is the data. Here's the code of a priority queue implementation. These are the constructors. The empty function returns true when the queue is empty, otherwise, it returns false. The insert function is to insert a record into the queue. The function pop is to delete the front, or toot, element, which has the highest priority, or lowest key value, of the queue and returns it. We will use this priority queue class to implement the construction of a Huffman tree. We will also discuss how to do this using the priority queue provided by the C, C++ standard template library, SDL. Here's the header file for implementing a Huffman tree. There are 256 ASCII symbols, with coded values from 0 to 255. We add an extra symbol called end of stream with value 256 to signify the end of the input sequence. So the total number of symbols is 257. H code is the Huffman code of a symbol. The variable n bits tells the length of the code word of the symbol. Node is a Huffman tree node. The class HuffTree implements a Huffman tree. Its function HuffCode will generate the code word for each symbol. The class HIterator is an iterator to traverse a Huffman tree. It is a friend of the class HuffTree. Here's the actual program. First, we include the source code of the priority queue, which uses templates and could not be linked. First returns the first node the iterator will point at, which is the root. The next write function returns the right child of the current node if it is not a leaf. The next left function returns the left child of the current node if it is not a leaf. A Huffman tree is constructed by the HuffTree class constructor. The counts, or occurrences, of the symbols are provided. In the constructor function, we create a priority queue of size 600 and the record data is a pointer to the node containing the symbol. The key will be the count of the symbol. We check the count of each of the 257 symbols, and ignore those whose counts are 0, which means that they never occur. We create a new node to hold the symbol. The record's data points to this node and its key contains the count, or frequency, of the symbol. We then insert this record into the priority queue. When we are done with the 256 symbols, which will be at the leaves of the tree, we set the symbol value to end of stream plus 1 equal to 157. which along with all larger values will be in internal nodes. We then retrieve two records that will have the least counts. We create a new node to hold a new record, whose count, or key, is the sum of the keys of the retrieved records. We merge the two records. The retrieved nodes become the left and right children of the new node. When the queue is empty, a single tree is formed and the last record deleted from the queue points to the root which is returned. The Huffman code of the symbols is obtained by traversing the tree recursively. We start from the member function Huff code. The application should provide an array, called codes here to hold the Huffman code words and the number of bits in each code word. We start from a code word of 0 and end bit 0 and call another member function Huff code to traverse the tree recursively. The variable code so far is the code word. If the symbol value is smaller than or equal to 256, the value of end of stream, we have reached a leaf. We then save the code word and the number of bits and return. Otherwise, we add an extra 0 to the code word by shifting it left by 1 bit and incrementing the number of bits, n bits. We then traverse the left subtree with the extra 0 added to the code word. We then traverse the right subtree with an extra 1 added to the code word by performing a bitwise OR with 1. Let us compile this program.
There's no error.
Let us consider a simple example of applying a Huffman code to compress data. We will read in data from a file, count the occurrences of each character, and then apply the Huffman code to encode the characters and save the code words in another file. To do this, we need some utility programs. We'll discuss these utility programs very briefly. In encoding or decoding the symbols, we need to handle them a bit at a time. So we wrote some utility programs to process bits. This program was written 30 years ago and was written in the old style, but this is not relevant here. There are many ways to write such programs, and you could write your own using the STL bitset class. The function input bit is to read in one single bit from the file. Input bits can read n bits from it. Output bit is to output 1 bit to the file. Output bits could output n bits to the file.
There are other utility functions that we need. The count base is to count the number of occurrences of a symbol in the file. Okay. And scale counts is scale down the counts if the counts becomes too large. And put counts is to save the counts of the symbols in the file, so that it can be reused to decompress or decode the compressed file. Get counts is to get the counts when expanding the file. Print code is for debugging, used to print the code out, the Huffman code. The file size is to find the file size of the file. Print ratio is to compare the input file and output file sizes. Encode is to encode the symbols with the Huffman code, okay, saved in the codes array. Decode is to decode the compressed bits using the Huffman tree. So this is the compress. They provided the input file and output file saved in their argv array. And this is uncompressed. Okay, this is usage exit message. Okay. And this is the make file. Let's compile this. Okay, so no error. So the executable is half x. Okay, so let's compress this file t. Okay, so we compile this as t. The output file is tc. C means compress. Okay, so the compression ratio is 67.0%, and now we can recover the file by decompress it. So t.c, so t.u. So again, the compare ratio is the same. Now let's compare these files. T okay, so T and T.U have the same number of bytes, and you could check using diff. Okay, and you'll find that they're the same. Okay, and T.C is the compressed file, which is only 67% of the original file. Now, we have implemented the Huffman tree using our priority queue. If you are interested, you could use the priority queue provided by the standard template library. In this case, you have to use this header, include queue. Okay, that includes the priority queue also. Okay, and then you need to define a class called PQ_node. Okay, to be pushed onto the priority queue, this node. Okay, let me uncomment this. Okay. To use the standard template library priority queue, you have to define this compression operator, okay, which is to be used as a function object, and this operator. So this will be the node pushed into the priority queue of the standard template library. And the others are the same. And here, so we don't need to create the priority queue ourselves. So we use the standard template library priority queue. It is called priority_queue. And so the first argument is PQ_node to be pushed. Okay, and we need to have a vector PQ_node, and then PQ_node, we called this priority queue to be QQ. Okay, that's how we use the priority queue. And these are the same. Now, instead of using insert, the standard template library uses push, which is our insert. Okay, so we need to push. And now their pop is slightly different from ours. They examine the first element using the function top. Okay, and then we move it using pop. There is the combination of their top and pop is our pop. Okay, so this was ours. So we comment this out, and so again, this was our pop. We comment this out. So this is the standard template library, top and pop, equivalent to our pop. And again, this will be, instead of insert, it should be push. And then the top and pop. Okay, others should be the same. So now let's make clean. Okay, so again we recreated the file, and we have this. Remove the t.c, remove t.u. Okay, and this is our new version using the standard template library to compress. So you get the same result. Now let's try the uncompression. Let's start by t minus e, t.c, t.u. So again, we get the same result. Okay, so you can use the particle we discussed, okay, in the last video to implement this, which is actually simpler, or you can use the standard template library particle, okay, which is more complicated. But either way it works. Okay. Well, thank you for watching.